So this shows a simplified architecture of the hack computer. With this part's actually the CPU. So all these parts within this grey box are actually inside of the CPU. So the ROM and the RAM are external to the CPU. So this makes up the entire hack computer. So we can see that internally the CPU is composed of the ALU, the A register, the D register, the program counter, and then various combinational chips, multiplexers, and so on. And this is a kind of top level interface of the CPU. So we can read data from the data memory. So this is essentially comes from RAM. We've got the instruction which comes from the ROM. There's also an external reset, so we can basically reset the computer. And then in terms of the outputs, when the ALU has done an operation, we might want to write that to memory. So this will connect to RAM. And then if we want to write to RAM as well, we need to we need to put this essentially a load bit. So this is the kind of load bit for RAM. And also provide the address. So these three parts all go to the RAM. And then the output of the program counter essentially goes to ROM. So we can see we've got some inputs coming from RAM and ROM, and then the outputs going to RAM and ROM as well. So there's this kind of various feedback within the computer. So we'll first look at the execute logic. So if the we know this is a kind of the fundamental makeup of an instruction. We do some computation, we can store the results in a particular destination and then do a jump if required. So if the computation contains M, M's obviously referring to the memory, so so if we're doing a computation that contains M, we need to read data from the RAM here. And then we know if the destination contains M, that means the output is going to be written to RAM. So if destination contains M, we're going to have some data coming out to RAM. We obviously need to set this to a 1 to be able to write to the memory. And then we also need to select the address as well. So if the destination contains M, we need to do something with these three outputs. That's a kind of fundamental execute logic. And the fetch logic, again, it's if we look back at the instruction, we know that instruction might contain a jump. So it does contain a jump. We can look at that by looking at the jump bits on the instruction. And then if reset is 0, so that means we don't want to reset the computer, and the ALU flags indicate that a jump should occur. The value of the A register, that will contain the instruction to jump to, so we'd essentially need to spit that out of the program counter. So the value of A would go out of the program counter, and that will then tell the instruction memory which instruction to output next. But if the jump shouldn't occur, if that kind of jump condition's false, we just have to increment the value of the program counter. So if we're on currently executing instruction 6, we'll just increment it 7, 8, 9, and so on. So in most cases, we're just going to be incrementing the instruction as we go through. But then if a jump does occur, look at the jump bits. Determine where the jump should happen. They might then have to jump to instruction 37, 38, and so on. But then if we do want to reset, this reset pin will be 1. And then the program counter then is set back to 0. So in the next cycle, it will just fetch instruction 0 from the memory and reset. So we need to look at the C instruction base. I need to decode these bits. So that's kind of what that's what the kind of decode logic is of the CPU. So we know that bit 15 is 1 for a C instruction, and it's 0 for an A instruction. So we don't have to use 14 and 13. We know bit A this tells us whether we're going to select between A and M, so we're going to read whether the ALU would do an operation on RAM or on the value what's in the A register. These bits, they go to the ALU, so this tells what ALU which computation to carry out. The destination bits then, so this tells us essentially where to pipe. These bits will tell us where to pipe the ALU output, so we can either write the output to A register, D register, or to memory, RAM. And then the jump bits will tell us which jump condition to carry out. So we need, you need to come up with the logic which decodes these instructions. So this is a kind of incomplete picture of the CPU implementation. So each of the C's here represents a control bit. So this means that somehow from an instruction, so an instruction is going to come into the CPU, and you need to come up with some logic to be able to decode that instruction. So depending on how you decode that, you will then determine which of these other C bits, control bits around the CPU, how they behave. So this comes from this decode block, but the decode block is not a chip part. So the decode block is not a physical chip. It's more this kind of series of combinational logic what's spread out from the CPU. But we'll just look at a couple of examples. So we know that, we look here, this A bit's here. So that is used to select between A and M. So it's not too hard to see that this multiplexer selects between A and M. So this control bit is essentially that A bit. So that would help tell us whether we're going to do the operation on A or M, for example. And then also with the ALU, we can see the ALU. The ALU output, it's piped out to the RAM. It also goes back into the D register, and then via this multiplexer it can end up going into A as well. So the kind of ALU output is kind of hardwired into this is M, into D and A as well. So depending on the destination bits, essentially we know whether we need to, the destination bits will tell us whether we want to write to memory, whether we want to write to the D register or the A register. And there's other, you can end up designing the other bits as well by looking at the instruction, seeing what each of the bits mean, and using them to implement all these control bits here.